Welcome back. In this video, we'll discuss section 17.2, when does the normal model work? In the last video, we considered taking a random sample of 25 Reese's Pieces candies. And what we wanted to do was determine the proportion of candies in that sample that were orange. So we computed the sample proportion, which we can denote by p hat. And because this is a number associated with a sample, it's a statistic. Now we're interested in determining or estimating the true population proportion of all Reese's Pieces candies manufactured by Hershey that are orange. We'll denote this population proportion with P, and it's a parameter because it's a number that describes the population. So we began to investigate the sampling distribution last time using the applet. This is the distribution of all the proportions from all possible samples. And we noticed that this distribution is roughly normal, mound-shaped and symmetric. It turns out we can use the normal model to model the sampling distribution or the distribution of the sample proportion if the following assumptions and conditions are met. One is the independence assumption, and under this we check a couple of things, the randomization condition and the 10% condition. So for the randomization condition, the data need to come from a simple random sample. And for the 10% condition, the population needs to be more than 10 times larger than the sample size. We should also check the success-failure condition, which says we should have at least 10 successes and 10 failures. So we need to check that NP hat is at least 10 and NQ hat is at least 10, where Q hat is 1 minus P hat. This ensures that N is large enough and that P and Q, which is 1 minus P, aren't too close to 0 or 1. Let's return to the Reese's Pieces example. Even though the sample proportion of orange candies varies from sample to sample, we saw in the last video that there is a predictable long-term pattern to this variation. Using our simulation, we needed to specify a value for the true population proportion P, but we have an important theoretical result that tells us what to expect for the shape, center, and spread of the sampling distribution without needing to use simulation. Here is that important result. It's called the central limit theorem, which I'll abbreviate CLT, for a sample proportion. It says, provided that the sampled values are independent and the sample size is large enough, we can predict three things about the sampling distribution of the sample proportion P hat. In terms of shape, the distribution will be approximately normal. For center, the mean will equal P, the true population proportion. And for spread, the standard deviation will equal the square root of PQ over N. We'll stop there for now.